Hello, Physics 1 students. I'm back with a video where I'm going to describe what happens when you have a pulley system, and we're going to wind it up or have it wound without slipping. We'll take it to be a very long rope, and then suspended down from that will be a mass. This pulley we're going to take to have a mass equal to little m, and we'll use capital M to refer to the falling mass. Similarly, we're going to say that the pulley has a radius, capital R. Now, we're going to analyze the motion of the falling mass. We're going to do it from two perspectives. First, we're going to use an energy conservation analysis to solve for the final velocity after it's fallen through some height, delta y. And then we will reproduce the same result by studying the torques and accelerations of the falling mass. So we're going to see the same problem. We're going to analyze it two different ways. So the first thing we want to note, though, is there's no slipping. So that assumption buys us a whole lot. It basically correlates the vertical motion of the falling mass with the distance traveled by a point on the edge of the pulley. So in particular, that allows me to conclude, up to a possible minus sign, that r times delta theta equals delta y. Let's think about the minus signs. If theta has a negative change, if it moves clockwise, then the mass will have a negative fall. So in fact, the minus sign should be as written here. So if theta is negative, delta y is negative, and vice versa. Similarly, we can say things like r times omega equals the velocity of the falling mass, and similarly, r times alpha equals the acceleration of the falling mass. That's what the no slipping condition allows us to immediately conclude. Okay, so let's analyze this problem from the point of view of from an energy perspective, and let's go ahead and assume that V initial is 0, just to make the analysis a little bit simpler. So it starts from rest, and then the object starts to fall, which causes the pulley, to rotate. So if I use an energy analysis, well, that always starts by first defining the system. So I'm going to make the system be the pulley and falling mass. All right. And then I apply the work energy theorem to this. So I would say the work equals the change in kinetic energy plus the change in potential energy. Now, work comes from outside forces acting on the system. The only outside force which acts on the pulley and the falling mass is gravity. And you know what? If I want to handle gravity using a potential energy, then I can just include that in my system, in which case there is no work. The work being done is 0. Okay, so there could have been a work coming from gravity, but because I'm going to decide to put it in with a potential energy, then I have to include gravity in the system, then there is no work. So now I just need to write down what this implies. So The only real trick is that kinetic energy is the total kinetic energy, and I have to remember that there are two possible types of kinetic energy, both linear kinetic energy in the falling mass and rotational kinetic energy in the pulley system. So I find 0 equals final kinetic energy minus initial kinetic energy. Well, since it starts at rest, the initial kinetic energy is 0. So that's going to be kinetic energy rotational final plus kinetic energy translational final. It's minus 0 because this is the initial kinetic energy. And then I have plus the change of potential energy due to the falling mass. Well, that's simply mg delta y. Proceed, I know the formula for this, but let's just write down the formulas for each of these quantities. The kinetic energy translational looks like 1/2 the falling mass, capital M, times the velocity squared. The kinetic energy of the rotational, the rotational kinetic energy is 1/2 I times omega squared. Now I need to tell you something else. We're going to assume that the pulley is a solid disk. So we're going to assume that that's a solid disk, in which case we have an explicit formula for the moment of inertia. It is simply, so this is going to be 1/2 times 1/2 the mass of the pulley, little m, times the radius of the pulley squared times omega squared. Just equating these. And there's one final simplification I can make. Because I know it rotates without slipping, I can relate omega to v. So I can write this as 1/4 the mass of the pulley, and I can write omega as v over r. So the r's cancel, and I get v squared. So let me rewrite this. I find that 0 equals 1/2 big M times v squared plus 1/4 little m times v squared plus mg delta y. Or turning this around, I can find that v squared, so the final velocity squared, equals just reworking this, I can say it's equal to minus mg delta y by moving this across the equal sign and divide by the coefficients of velocity squared. So I'm going to get 1/2 big M plus 1/4 little m. And if I want to clean this up just a little bit, I could write this as minus 2 mg delta y over capital M plus half lowercase m. Now, if we remember our kinematic equations, so this is our formula for the final velocity squared. If we remember our kinematic equations, which say that, specifically kinematic equation 3, says that v final squared equals v initial squared plus 2 times the acceleration times delta y. And if we remember, and that applies whenever the acceleration is constant, and in this case, that will be true. So we learn just from kind of pulling out numbers that it must be that the acceleration is going to be minus little mg divided by, oh dear, I have to go back. Sorry guys, I made a mistake. When in the potential energy, you have to be careful with which mass. The object that falls due to gravity is the large mass. So this should be a capital M. I apologize. And I have to chase that through. This is a capital M, in which case this is a capital M, in which case this is a capital M, in which case this is a capital M. Okay, sorry for that. Now we're cooking. And then the rest of the denominator becomes big M plus little m over 2. You can do a couple checks here, and that's actually how I knew I'd fouled it up. If the little mass, the mass of the pulley, is 0, if it rotates for free, this goes away, and in fact, you just get that the falling mass falls with the universal gravitational acceleration minus g. On the other hand, if the pulley had a huge mass, if the lowercase m went off to infinity, well, then it's the same as hooking the rope up to a wall and nothing moves, and so this goes to 0. So it checks out. We're going to see the same result come from an analysis of torques and acceleration. So let's see how that plays out. So here we're going to have the same system from a force or torque perspective. So let me go ahead and draw that. I have my pulley, and then I have a rope, and we're going to assume that the mass block is down here and has mass capital M, and the pulley has mass lowercase m. It has a radius r, and we're assuming that the initial velocity is 0. So, and I'm going to go ahead and mark the axis of rotation, which would be in the middle of the pulley. So in this case, it's a little more complicated, but we'll get to the same answer. We have 2 objects, so we're going to have 2 free body diagrams. Let's start with the simplest one. For the large mass object, well, there it is. There's no rotational motion relevant for this, so we can ignore the details of the body and just write it as a point and say that the upward forces will be a tension and the downward forces will be a weight. And that's it. So I can write the net force in the y direction is equal to T minus capital M times G, and that will equal the mass times the acceleration of the falling object. So this is my first equation. We're trying to solve for the acceleration. The givens were the masses and the radii and things like that. So we don't know the tension. So that's an unknown. So I have one equation, I have 2 unknowns, so I need another equation. That's going to come from the pulley. So for the pulley, I need to remember the geometry because this is going to have a torque. In fact, so the pulley is not allowed to actually move. It's pinned down. So I don't really care about the net forces because I know that the normal forces are just going to do whatever it takes to make everything add up to 0. But I do care about the net torque. So I'm going to study rotations about this axis of rotation. Any normal forces that are generated at that axle will give no torque because they have no moment arm. However, I do have a torque coming from the rope that hangs down. So kind of draw it in there. The lever arm is going to be the radius, and then the force going down is going to be the tension. And I can immediately see that's going to cause a clockwise rotation. So the net torque is going to be a negative number. So the net torque equals minus tension times R, because T is the magnitude of the tension. It's a positive number, so I need an explicit minus sign to make this all work. And that should equal I times alpha, where I is the moment of inertia for this disk. We know that. And alpha is the angular acceleration. Let's write that out a little bit. So the torque net equals I alpha. That means minus the tension times R equals the moment of inertia for a disk is 1/2 the mass of the disk, which is lowercase m, times the radius of the disk squared, and then we have to multiply by alpha. And I also have my other equation for the falling mass, which said that tension minus big mg equaled big M times A. So right now I have let's count unknowns. I have the tension is unknown, alpha is unknown, and A is unknown. So I have 3 unknowns, and I have 2 equations. But as with the kinetic energy condition, the rolling without slipping comes in to save us. No slipping says that R alpha equals the acceleration. And let's worry about minus signs. Well, it's the same as last time. If alpha is negative, acceleration is negative. If alpha is positive, acceleration is positive. So they have the same sign. That allows me to convert this equation into something involving tension and acceleration. So I can say minus T times R equals 1/2 the mass times R squared times A over R. Or turning it around, I get minus the tension equals the mass of the pulley over 2 times the acceleration of the falling mass. Great. So I can take this equation, substitute it in here for tension, and I get minus little m over 2 times A minus big M times G equals big M times A. I'm going to rearrange this equation to write this as minus big M times G equals A times big M plus little m over 2, or A equals minus, I feel like I forgot a factor of 2 somewhere. Well, maybe not. Just push through. I'll check in a minute. So that's simply going to be big M times G over big M plus little m over 2. Nope, that's right, because that has the correct limits. If I make the pulley mass small, the object goes over to free fall. That's good. If I make the pulley mass large, the acceleration goes to 0. This is the same answer we found before by thinking about kinetic energies. So this is kind of a nice little example which shows how you can apply kinetic energy you can apply rotational motion both to energy and force torque kind of problems. And the answers, of course, are always going to be compatible. All right. So that's all for this video.